In this video, I'll try to explain some details and tests related to the heating and cooling actuators of the Wi-Fi Reflow oven. There are two new elements that have been added to the last video's wiring diagram for implementing the cooling system. The first is a contraption for opening and closing the oven's door, and the second is a set of fans that are meant to force the airflow when the door is open. In the following section, I'll be showing the construction and installation of those elements. After several hours, all the parts are printed. The link between the servo arm and the slider is a bent piece of 2mm rod. The first thing to do is shape it following the template. Although the pliers are not the best tool for this task, I am trying to keep the shape as planar as possible. After finishing, it's only necessary to trim the edges and file them. After having collected all the parts, I'll start assembling the door pusher. The adjustable joint for the pusher bar has the nuts embedded in its body. The bolts have to be tightened when everything is in place. The pusher end has a pressure fit and has to be assembled using a hammer. Now that everything is in place, the radio control servo can be installed. The hole in the servo arm has to be increased to a diameter of 2mm to fit the link rod. The shaft sleeve prevents the rod to fall apart. In order to adjust the servo, it has to be powered and connected to the control circuit with a minimum set point value. At this moment, the servo arm has to be fitted with the pusher at the minimum position. After some tests, the screw of the servo arm can be assembled. The next step is marking and drilling the holes for attaching the pusher to the control box. With the pusher in its position, it is possible to cut the aluminum tube to the right length. The aluminum tube is attached to the oven door handle with some cable ties. Now the final adjustment can be done. With the door closed and the set point of the servo to the minimum, the pusher has to be touching the aluminum tube. Once it's set, the screws of the slider can be tightened. For the fans holder, I've made a template that can be downloaded from the link in the description. First, it's necessary to cut the template and later stick it to a prototype board. I've used painter's tape to remove it later without any problem. The fans are wired in parallel. After finishing assembling and wiring them, the next step is to attach the fans holder to the oven. As described in the previous video, the heating control is based on a solid-state relay. Internally, the solid-state relay uses a triac as the commutation component. Apart from the triac, it contains a driving circuit that provides an easy control interface and electrical isolation. The isolation generally is achieved with an optocoupler. According to the specs, any DC signal above 3 volts will make the relay connect its high voltage terminals together. The neutral is connected directly between the mains voltage and the oven, but the live wire is connected or disconnected by the triac. The control circuit is providing the control signal. The triac can be turned on at any time, but it only turns off if the control signal is less than 3 volts and the input voltage reaches 0 volts. This means that when the control signal goes to 0, it won't disconnect the load until the end of the current semicycle. In Europe, there are 100 semicycles per second, and in America, 120. For modifying the power applied to the oven, turning on and off the solid-state relay in a pulse width modulation fashion is alright. The period I've chosen for the PWM is 250 milliseconds. That is a speed much faster than the oven dynamics. So it can be said that if the ratio between T on and the period is 50%, the power applied will be half. The only thing to consider is that in the range from 0 to 100%, there will be 25 discrete steps, 30 in America. The door opener uses an RC servo. It is a kind of standard actuator among makers and hobbyists for cheap and steady mechanisms. Although it's not super precise, it's good enough for this application. The servo has 3 connections: the ground, the positive voltage, 5 volts, and the control signal. In order to give a position set point for the servo, it's necessary to provide a PWM signal with a period of around 20 milliseconds with an on time that varies between 1 and 2 milliseconds. The duration of the on time indicates the angle. In this system, minus 100 will mean 2 milliseconds. That is, the door opened at the maximum the actuator can. With the minimum firmware done on the oven side and a small Python script in the computer, now it's possible to send any set point between plus minus 100 and read the temperature every 250 milliseconds. The first test to do is performing an open loop step response. The oven has a built-in thermostat with a maximum set point of 250 Celsius degrees. This could be considered the saturation of the system. In order to be far away from the saturation point, a step of 15% of heating power has been applied. The response is similar to the one of an overdamped second-order system. This result is going to be used to estimate a model of the oven's transfer function that will serve to calculate the controller parameters. In order to observe the response of different actuators configurations, a very good option is setting up a closed-loop controller with just a fixed gain. Every time a new temperature is measured, the new power set point that is sent to the oven is obtained subtracting the measured temperature to the set point and multiplying it by the gain. The tests have been performed always with a gain of 5 and a set point of 150 degrees. The first test has been carried out only with the heating elements and a try that came with the oven inside the oven. This controller stops heating at the moment the temperature exceeds 150 degrees, but the actual temperature reached due to the thermal mass goes up to 210. The next test is the same as the first one, but removing the tray. The overshoot is much smaller. This demonstrates that the thermal mass is something to take into account. The third test includes the oven door controller. As the set point can be negative, the overshoot is smaller and the response is much more symmetrical. The fourth test adds the fans that are always on to the cooling actuator. The effect of the fans is not appreciable. The fifth test is the same as the fourth, but in this case the fans are mounted with smaller spaces. It reduces the overshoot slightly. In the sixth test, the PWM signal to the servo of the door opener has been modified to provide a wider pulse and being able to open the door a little bit more. Again, the improvement is very little. In the last test, a logarithmic converter of the set point to the door opener servo has been added. This is meant to compensate for the smaller quantity of movement of the pusher at the beginning due to the servo arm position. The improvement in the overshoot is very little, but the natural frequency has been increased. This indicates the effect is more noticeable with small signals. As a conclusion, definitely the door opener has a very big impact as demonstrated in the third experiment, and if the thermal mass could be reduced more, the response will be better as demonstrated in the first experiment. I won't try to insulate better the chamber of the oven. Instead, I will choose to use the configuration of the last test to continue with the project. Being said that, the configuration that includes just the heating and the door opener may be good enough.